Starting from this video, we will explore deep learning. In the deep learning course, we will take a closer look at the following 8 topics. The first topic is Artificial Neural Network, ANN. Since ANN is the basic framework for deep learning, let's look at it in relative detail. The second topic is various techniques designed to improve the performance of artificial neural network. Many techniques have been developed over a long period of time. The third topic is Recurrent Neural Network. It mainly learns sequence data such as time series. In the fourth topic, we will look at attention networks. They are mainly used in natural language processing, NLP, but we will apply them to time series prediction in this course. We'll look at them in more detail later in the NLP course and use them to create machine translator or ChatBot. The fifth topic is convolutional neural networks, CNN. We will implement 1D, 2D, and 3D convolutional neural networks, and also implement a convolutional LSTM. The sixth topic is autoencoder. We will apply this to dimensionality reduction, noise reduction, and outlier detection. And also look at variational autoencoder, VAE, a generative model. In the seventh topic, we will look at GAN, generative adversarial networks. Let's look at various GAN models such as DC GAN and unrolled GAN. Lastly, we will look at unsupervised learning using deep learning. Let's implement a network that performs clustering. Using Hebbian learning rule, competitive learning model, etc. Now let's look at the first topic, artificial neural networks. This video is part 1 of a series on artificial neural networks. This video was produced in Korean and translated into English. My voice was generated by AI text-to-speech. Let's take a look at the full table of contents of artificial neural network. In Chapter 1, we will briefly review the history of AI. In Chapter 2, we will look at the structure of ANN. Let's look at the basic structure of ANN and the prediction process of ANN. And let's look at the objective functions, MSE and cross-entropy. In Chapter 3, we will look at how to train an ANN. Let's learn about gradient descent, which is widely used throughout deep learning, and how to obtain the gradient. In Chapter 4, we will implement the ANN. Let's implement ANN in an approximate way using numerical differentiation. Automatic differentiation allows an accurate implementation of an ANN, which we will see later. And we will implement the ANN for linear regression and nonlinear regression. Now let's take a brief look at the history of AI. AI has a long history and has gone through several booms and winters to reach what it is today. The first paper to approach artificial intelligence through neural networks was Warren McCulloch's A Logical Calculus of the Ideas Immanent in Nervous Activity, published in 1943. They introduced the concepts of logical neurons and neural networks. At that time, the logical neurons had no concept of learning and only had instinct to operate as they were created. In 1949, Donald Hebb created the first learning rule that could train neural networks. Hebbian learning rule is available to supervised learning as well as unsupervised learning. Later, we will write a code that performs clustering using unsupervised Hebbian learning rule. In 1951, Marvin Minsky applied Hebb's ideas to create a learning machine that operates with motors and vacuum tubes. This machine is SNARK, which is a randomly connected network of approximately 40 Hebb synapses. This was the basis of his doctoral papers, Neural Nets and the Brain Model Problem, in 1954. In 1956, the Dartmouth Summer Research Project on Artificial Intelligence was held. This event is widely considered the founding event of artificial intelligence as a field. One of the founding members, John McCarthy, was the first to use the term artificial intelligence. In 1957, Frank Rosenblatt published pioneering work on the first supervised learning algorithm for neural networks, known as the perceptron. He implemented the perceptron for binary classification using the delta learning rule. The perceptron was considered to have finally paved the way for artificial intelligence. It was a time of great change and innovation of AI. However, it was later discovered that the perceptron at the time had certain limitations. This was because perceptron worked only with linearly separable classes. In 1969, Marvin Minsky and Seymour Papert mathematically proved the limits of the perceptron in their book, Perceptron. This publication led to a decline in AI research. During this period, Malzberg, Grossberg, Fukushima, etc. published competitive learning rules. This was a learning method that was slightly different from existing learning rules and closer to the brain's learning principles. Teubo Kohonen published Self-Organizing Map in 1984, an interesting neural network model that used the instar rules published by Grossberg in 1974 and further developed competitive learning. These methods can be used in unsupervised learning. Later, we will look at how to cluster MNIST images using the self-organization map. In 1986, David Rumelhart created a multi-layer perceptron by applying the generalized delta learning rule. This overcame the limitations of the perceptron previously pointed out by Marvin Minsky. At this time, AI research began to boom again. However, the AI boom did not last long, and AI winter came soon after. Both private investors and governments lost interest in AI and stopped funding it due to high costs relative to seemingly low returns. This led to reduced research funding, and as a result, few breakthroughs had been made. Despite the lack of funding during the AI winter, the 1990s saw impressive progress in the field of AI, including IBM's Deep Blue in 1997. During this period, a new paradigm called intelligent agents became widely accepted. As interest in AI grows again, research funding had also increased, allowing for more progress to be made. Since then, deep learning technology has developed remarkably. Today, it continues to advance at a very rapid pace. Regression and classification problems can be expressed in the form of a feed-forward network. To learn from such data, in machine learning, we mathematically generate a linear or nonlinear regression model and fit the model to the training data to estimate the parameters W and B. We then use this model to predict the target value for the test data. The same goes for classification problems. Using a network model like this instead of a mathematical model can also solve the regression or classification problems. This network can be applied to linear regression problems. This is called a node or vertex, and the connection between two nodes is called an edge. There is an input layer where the data is input, and an output layer where the results are output. Data points are input into the input layer one by one. The input value is multiplied by the edge value, and the added value is output. Then the output will be this value. This is identical to the mathematical model on the left. This network can be completed by fitting it to the training data and determining W and B. This is the process of training the network. When test data is input to the trained network, the predicted target value of that test data will be output. A network for solving nonlinear problems can be built like this. An intermediate layer is placed between the input layer and the output layer, and all nodes are fully connected this way. Then, the number of parameters increases, and results in complex forms are output, making it possible to use it as a nonlinear model. Of course, for this to be a nonlinear network, it needs a nonlinear activation function. We'll look at this later. Applying these networks to regression and classification problems has many advantages. Even small changes to the mathematical model make it difficult to solve, but the network model can be modified to any extent. For example, if your data has multiple target values, you can increase the nodes in the output layer of the network. And if you want to create a more complex model, you can increase the intermediate layers or increase the number of nodes in the intermediate layers. This is the basic idea of artificial neural network. However, the issue is how to determine W and B. Now, let's look at the basic structure of the artificial neural network created based on the network on the previous page. A simple drawing of the biological neuron system looks like this. There is a cell body or soma, dendrites that receive information from other neurons, and axons that are the output. There are also synapses that control the amount of information passed between neurons. Artificial neural networks are applications of feed-forward networks and neural systems. The basic structure of ANN is as follows. There is an input layer that receives data, and there are multiple hidden layers for nonlinearity. This figure has only one hidden layer, and there is an output layer that outputs the results. Each layer has multiple nodes. The number of nodes in the input layer is determined by the number of features in the data. And the number of nodes in the output layer is determined by the number of target values in the data. This ANN has a total of 9 nodes. These are the node numbers. Each node corresponds to the cell body of a neuron. The input of each node corresponds to the neuron's dendrite. And the output of each node corresponds to the axon. And there is a connection weight between each node. This corresponds to the synapse between neurons. And biases are connected to the nodes in the hidden layer and output layer. Let's take a look at each component of ANN. This is an artificial neuron. The cells in the input layer pass the input signal as is to the upper node. The cells in the hidden layer and the output layer add up all the input signals received from lower cells. Convert the result using function f and output it. A bias cell is connected to each cell in the hidden layer and output layer. This always outputs 1. Each node is connected to each other by weights. The output of the lower neuron is multiplied by the weight and passed to the upper neuron. The weights W and B can be considered the synaptic gap, i.e. the small gap between the output of the lower neuron and the input of the upper neuron. When W or B is small, i.e. when the gap is wide, only a small portion of the information from the lower neuron is passed on to the upper neuron. And when W is large, i.e. when the gap is narrow, much of the information from lower neuron is passed on to the upper neuron. The total amount of information input to the node 6 can be calculated as follows. Wij denotes the connection weight between the node I and the node J. And the bias Bij is also the connection weight between the node I and the node J. If W06 is 0.1, only 10% of the input signal X1 is passed to the upper node. If W16 is 0.9, 90% of X2 is passed to the upper node. Passing a lot of X means that the signal is important. The size of this input is X1 times W06. The size of this input is X2 times W16. And the size of this input is 1 times B26. The sum of these inputs is the total amount of information received by node 6. The activation function in each node controls the size of neurons' output. Neurons in the hidden layer use nonlinear activation function, and neurons in the output layer use linear or nonlinear activation function. Using the activation function, the output of node 6 can be expressed as follows. Next, let's look at the activation function in a little more detail. The following types of activation functions are widely used. Activation function is used to convert the output size of a neuron into a desired range of values. For example, in binary classification, a sigmoid-like function is used in the output layer, because the output value must be between 0 and 1, or between -1 and +1. And in regression, a linear function is used because the output value should not change. Another purpose of the activation function is to introduce nonlinearity into the hidden layer. If you do not use an activation function or use a linear function in the hidden layer, the network behaves as a single-layer neural network for linear learning. Therefore, for nonlinear learning, a nonlinear function must be used in the hidden layer. ReLU, TAN, Leaky ReLU, SoftPlus, etc. are used in the hidden layer for nonlinear learning. In particular, ReU is most widely used in hidden layer. So far, we have looked at the basic structure of artificial neural network. In the next video, we will look at the basic operation process of ANN. Let's look at the prediction process and the objective functions for learning.